welcome everyone to this math reading group on optimization. It's been a while, and unfortunately, it may be one of the last, but I like reading groups. I'm not sure. Anyway, so we'll be talking about convex optimization. So essentially, today is mostly basics theory about optimization in machine learning, but really more optimization proper, because the kinds of optimization problems we have in machine learning are not the nicest ones, the nice ones to study and theoretically, but there is quite a lot of theory in optimization about the nicer problems which you don't have in machine learning, and the things you can know about these nicer problems can still tell you a little bit about what you could hope for in the general case. So I like to start with notable anniversaries. So today is the 23rd of March. It's the birthday of Pierre-Simon de Laplace, who was a French mathematician, famous for doing all kinds of stuff, but notably he was basically the first Bayesian. Like, he was one of the first people to formalize or develop a theory of probability and to have this Bayesian interpretation of probability. The other interesting, to me at least, event on March 23rd was the birth of Emmy Noether, German female mathematician. She basically developed the whole modern theory of algebra like rings and fields at the beginning of the century. She did a ton of interesting work, also linking symmetries in physics and conserved quantities in physics. So both are really interesting people. If you go look at like the Wikipedia page of stuff that happened on the 23rd, there's quite a few less nice events, but at least I could pick those two. Right, so the menu today is basically a bit of setup of a basic learning theory of, okay, we have a supervised learning problem. What is the optimization problem we're trying to solve? How we're trying to formalize it? And then the main bulk of the session is going to be looking at convergence rates of classical algorithms like gradient descent, stochastic gradient descent, and so on. Mostly in the nice, easy convex case and some variations. And then very briefly, we'll talk about what we can say about the non-convex case, which is not a lot, unfortunately, but we'll see at least some things. And as a side note, so pretty much all of my material today comes from Bax, so Francis Bax's book, Learning Theory from First Principle. It has all the proofs, which I omit here, and a lot of details, so I thought it was a pretty good book of like basic learning theory along with some modern optimization stuff. Okay, so the generic supervised learning setup, we probably all know it at this point. We have some probability distribution xy over some sets of spaces x and y. So here big X and big Y just means random variables that come as a pair. So I have a joint distribution of inputs and outputs, say, and I want to find some map f from my input space to output space such that roughly f of x is approximately y in some rough sense for x and y sampled from this big xy distribution. And the way like classical learning theory formalizes that is to say, well, let's suppose we have some loss function L that basically takes my prediction f of x and compares it with the true value y and tells me how good my prediction is. And then because we have a distribution over x and y, we can essentially try to ask what is the expectation of the loss of a random input and output pair when gone through f. And so looking at this expectation, it's computable, and learning theory, it's called the expected risk. And it roughly measures how good a given function f is at estimating the relationship between input and output. And turns out we sort of have an actual like optimal solution, at least theoretically, that we usually can't compute it, namely the Bayes predictor, which simply, assuming you have the full information about your distributions, you just take the minimum of this expectation here of x prime over z, and take that for any x, and that's called the Bayes predictor. So if you imagine that this is a binary classification problem, the Bayes predictor will just predict whichever class has the highest probability for x. And so often we note R star for the optimal risk, so the optimal value that we could hope for in this problem. Now, unfortunately, and this is getting closer to the actual setting, well, we don't really have access to this distribution here. We only have some finite number of samples, let's say n samples, x of y, and we assume that they're sampled independently from this is wrong with this xy distribution. And so we can still like estimate or approximate this expectation by simply taking the empirical mean of the loss over my sample, the input-output pairs. And so this is called the empirical risk, and because that's all we have, we use that as a proxy for the expected risk. And so now, assuming I have like some parametric family of model f theta, so I have a family of maps, and their value is determined by just a set of parameters theta. And let's say I also add some regularizer omega that somehow lets me distinguish or discriminate between different equivalent sets of parameters, let's say. So the general optimization problem then becomes minimizing f of theta, which is simply the empirical risk plus the regularizer, which I could have just no regularizer, maybe the norm of theta, and that would be something we have. So that's the general setting, but of course this is an optimization problem, so we want to solve it using an optimization algorithm. But before getting on to the brass tacks, a quick word. So suppose I run some optimization algorithm to solve this problem, and I get f of theta hat as a result. So I'm not guaranteed to get like the absolute best solution. So if I compare the gap between the f theta hat and the absolute minimum I could get searching through the entire search space or parameter space, I can do a little trick and decompose this into three terms. And so notice here we first have the gap, the distance between the empirical risk and the expected risk for f hat or theta hat. And on the bottom, the same thing for like this f theta star, which is like the optimal solution. So like both these top and bottom terms is just like estimation errors that we get from only having these n samples and estimating the expectation by the empirical mean. So these, both by the law of large numbers, they're roughly O over 1 over square root of n. And so the middle term is what's interesting here is just the gap between, well, the expected risk for theta hat and the absolute best expected risk. But note that this may not be like, it doesn't need to be the Bayes predictor. It doesn't need the absolute optimal predictor over all functions, but over this restricted class of functions that we have. And so this term is called the optimization error, and it's basically what we're trying to optimize here. And so the conclusion from the discussion is that because we know that these terms add about like 1 over square root of n error, we know that this term doesn't need to get much lower than that. So usually 1 over n, or oops, I think it needs to be 1 over square root of n, one of these. So that's basically the optimization they're trying to target here, basically 1 over n or 1 over square root of n, where n is the size of the data set. Okay, so now to actually talk about an optimization algorithm. So the classical one is gradient descent, which given some initial like guess for the parameters theta 0 and some step sizes gamma t, and they're chosen in advance, we'll simply do theta t is equal to theta t minus 1 plus gamma t, the step size, plus the gradient times the gradient, at theta t minus 1. So this is the general algorithm, and in most non-machine learning cases, this step size gamma t is chosen on the fly by something called a line search. So basically, you have this secondary problem of you have your gradient, which tells you, okay, go this way and the loss will go down, and you're leaving from theta minus 1. And so basically, you're trying to optimize this one-dimensional problem of what is the optimal step size. And one-dimensional optimization problems are easier to solve, and so in most cases, it's practical to do that. And some practical line search algorithms use, again, not in ML, or stuff like backtracking or the Armijo condition. So if you're interested in these, you can look them up. But in that is within the non-machine learning world. In machine learning, specifically neural networks, well, you have a nasty optimization problem, which is not convex, which is not exactly smooth in technically, or not even strictly differentiable if you're using value networks. And so really these line search algorithms won't work really well. And so that's a sad thing, and or they won't work really well, or they will just be way too expensive. So we can't really use those. But it's still interesting to show an actual example of atomimal, not even neural networks, in this case, so ordinary squares. So let's suppose I have some matrix R, so phi size n times d, and I have my output vector y. And I want to minimize this expression here, which is simply, I'm assuming that there's a linear relationship between theta and y, so, or big phi and y. So theta here is just a set of linear parameters, and I'm basically just doing linear regression to predict y from theta, or from big phi, sorry. And so this is actually a nice function because it's convex, it is quadratic, so it's basically a linear system to solve, and so it's really easy. And if we solve this with using gradient descent, it's not the optimal way to do it, but it's still interesting. So the gradient is simply this expression on top, and the most interesting part is the Hessian of this function, because it's twice differentiable. It is simply this covariance matrix phi of t times phi. And the important bit about the Hessian is if you look at its eigenvalues, let's say the maximum eigenvalue is big L and the minimum eigenvalue is mu. And then we have this number k or kappa, which is L over mu. It's usually greater than 1. And kappa here is basically going to predict how well or how easy to solve this problem is going to be. So it turns out that actually, because it's basically a linear system, gradient descent, just you can find the exact solution for this problem. So even if I remove like the norm here, it says theta t minus theta star, the optimal solution, is I minus gamma h, this Hessian here, to the power of qt. Imagine I have just like parentheses here, times my initial guess minus the optimal solution. And so if I turn this into norm, this tells me, okay, the distance to my optimal solution theta star is basically this number to the power of 2t times my initial the initial distance between theta 0 and theta star. And so how to, like, assuming we choose gamma to be constant, which we can do, how to choose the best gamma basically depends on the spectrum of H. And so because the eigenvalues of H are between mu and L, well, it turns out that the optimal choice of gamma here is just 2 over mu plus L, in which case we get the following rate, which it's not super clear how good it is, but this is a faster convergence rate than what we have on the bottom. So notice here we need to know about the lowest, the smallest eigenvalue mu, but it might be that actually mu is equal to 0, right? If the matrix is not strictly invertible, or it might be too expensive to compute, so maybe we only know L. And so in this case, we can be a bit more conservative and just take 1 over L, just assume mu is 0. And in which case we still get another convergence rate of 1 minus 1 over kappa times 2t. And notice here that this is basically just an exponential convergence rate, right? We know that if we do this many additional steps, we will get an exponential reduction in our error. But it depends on kappa. If kappa is close to 1, it's called a well-conditioned system, and then this is basically a very small number to raise to the 2t, so it's very quickly very slow. But if k is large, if kappa is very large, then we basically have something equal to 1, and so it's much slower. We can also look at what's this convergence rate looks like for the function values, right? Because we don't know what the optimal solution is, and so we can't really know what the distance to our initial guess to the optimal solution is, right? Instead, we can only look usually at the actual function values. And so this is a bit more interesting. If we know, let's say, that the optimal solution would have value 0 here, then this is more interesting because it says the distance between the gap between the function value at step t and the optimal function value is again bounded by the same 1 minus 1 over kappa to the qt. And actually, we can bound this a bit more by just the exponential of minus 2t over kappa. And this is a bit nicer. And we see a much more actual exponential convergence rate. We can get another convergence rate for the function values, this time again in terms of the distance between the initial guess and the optimal solution. But here it's just L over 8 times t, so it's not exponential, it's just 1 over t. But still, we at least we have some guarantee that if we perform the gradient descent for long enough, we will get arbitrarily close to the actual solution, or a actual solution. So this is a figure from the book, which shows the influence of the actual eigenvalues over the solution or the gradient descent here. So we have the optimal, the bound on the top, and you can see it's quite far from the other curves. And the blue curve here is obtained when the eigenvalues are proportional to 1 over k. So you get 1, 1/2, 1/3, and so on. And you can see that in this case the conversion is pretty fast. Whereas if we take the eigenvalues to be 1 over k squared, it is much slower, and basically we get a very fast decrease at the beginning, and then it slows down. And the reason for that is that as your optimization process goes on, the dominant part changes from the highest parts of the spectrum. So at the very beginning, you get the most decrease from the higher eigenvalues, so let's say 1, so you get a very fast decrease, and then as you progress, these high eigenvalues are just no longer important, and it's only the lowest eigenvalues. And so if you have a lot of very low eigenvalues, which is more the case in the case of 1 over the k squared part, most of them would be close to 0, then your convergence fit is going to be much lower. Okay, and we have an example over the same plot over logarithmic scale. Okay, so I'll be mentioning more about not quite the eigenvalues, but this sort of ideas a bit later. So this was just a simple example, right, of ordinary least squares. But the more general setting for these kind of results is basically assuming that the function we're optimizing is convex. And so convex in this context means for a differentiable function that if I look at theta and take the Taylor expansion around theta of order 1, right, so it's f of theta plus f prime of theta times eta minus theta, then this is lower than the actual function value. Note that if f is twice differentiable, then convex is simply equivalent to the second derivative between being positive definite. So this is what this notation here means. You might know another definition of a convex function which does not rely on differentiability. It says that f of alpha theta minus plus 1 minus alpha eta is smaller than the convex combination of these two values. And this is just the special case when f is also differentiable. And the nice thing about being convex is that we have a bound on the function error, which is quite useful. So we know that f of theta minus f of theta star, where theta star as always means the optimal value, it is simply lower than the gradient f of theta times theta minus theta star. This is somewhat nice because it means that we know that if we are fairly far away from the optimum, well, this is going to be large, and assuming the gradient is not too small, then we go pretty fast to the optimum. We have better solution. There will be better conditions for that a bit later. So we can have a stronger notion of convexity called strong convexity. And it's basically the same idea as convexity, but you add, you add a norm in addition. So f is called mu strongly differentiable if and only if we have basically convexity when adding an additional, like the norm between, or the distance, if you will, between eta and theta times some rate or factor mu over 2. And the interpretation, and this might look like to you a bit like just ridge regression or ridge regularizer, and it's basically what happens when we do ridge regression. So the nice thing about that is that if f is twice differentiable, this just means that the second derivative is larger than mu I, and that just means all the eigenvalues of my second derivative have to be larger than mu. So I have a lower bound on the spectrum of the second derivative. And then we have sort of the reverse relationship. We see that f is else move if when I take this expression, which is simply the first order Taylor approximation of f, it has to be smaller than L over 2 times the distance between theta and h. And so if I combine all these properties, I have some nice guarantees for optimization. So namely, if f is convex and differentiable, then I know that theta star is going to be a global minimizer if and only if it is a stationary point, so the gradient is 0. So that's a very nice property. If, in addition, I know that f is mu strongly convex, then there's only one global minimizer. And then some other properties. So there's a relation between strong convexity and just convexity. Basically, you take a convex function and add the norm mu over 2, and it becomes mu convex or mu strongly convex. We have some other nice things. So if mu is strong, f is mu strongly convex, then we have a lower bound on like essentially the norm of the gradients, essentially. So we have something like this. A nicer property is the next one. So if f is mu strongly convex, that the actual norm of the gradient has to be larger than mu times the difference between my function values. And this is actually really useful because it means that if theta is very far away from the optimum, like f of theta is very much larger than this, then it means that the gradient norm must be large at this point. And so if we're far away from the optimal solution, the gradient is large, and so we go faster towards the optimal solution. And then, so the synthesis of like this property and this property, if f is mu strongly convex and L smooth, then I have both a lower bound and an upper bound on the spectrum of the Hessian here. And this is going to be quite useful. So if we look at the actual like results, again without proofs, so if for gradient descent, if f is L smooth and mu strongly convex, then doing gradient descent with this 1 over L step size gives us the following convergence rate. So the gap between the function values between the t, the estimated time t, and the optimal theta is going to be this exponential of minus t over kappa times the initial error. And kappa again here is just L over mu is the condition number. And so ideally you want kappa to be as close to 1 as possible. If we don't have the mu strongly convex but just convexity, then we get again a slightly weaker rate, basically 1 over t times some constant. Okay, and like the classical illustration about the condition number which you might have seen, so assuming that this is like either a linear model or a linearization of your loss function around some point, the condition number, right, is the largest eigenvalue divided by the smallest eigenvalue. And because the Hessian is going to be a symmetric matrix, it means it has orthogonal eigenvectors and positive real eigenvalues. And so the largest eigenvalue is just going to be the like how stretched in a direction is this local loss function, and mu is going to be the smallest direction. So here, like L over mu, L mu are quite close to one another, and so the condition number is close to 1. And so in this case, gradient descent goes pretty fast to the minimum. The other case is if I have a direction where I stretch a lot and another direction where either I don't stretch a lot or even I compress, then the condition number is going to be very large, and then in this case gradient descent has a lot more trouble, it needs to take a lot more steps. And so like this is just a generic thing to care about whenever doing optimization, is how well conditioned my problem is. If it's really poorly conditioned, I can really like wait quite a long time before getting any progress. And so you have some techniques like preconditioning or stuff like that involving like in adaptive methods essentially to improve this condition number. as sort of quick another trick before moving on to SGD, we can look at Nesterov acceleration. So Nesterov acceleration, it's a clever algorithm that sort of handles also these problems with the condition number. And if so, for F mu strongly convex now smooth, we have the following algorithm with two state vectors. And it's basically a fancy modified momentum term if you look at it closely. And the nice thing about this is that we get a convergence rate of some constant L times the initial error times 1 minus 1 over the square root of kappa times t. And this is nice because we had like kappa here, but here we only have square root of kappa. And so this means that actually if in the first case we'd need like roughly kappa or 1 over kappa, just kappa iterates to converge, then here we only need square root of kappa. So if like the condition number kappa is really large, this is a nice speedup. And it's why also stuff like momentum like in Atom and other methods are quite popular in machine learning. Okay. Any questions before moving on to SGD? Okay. Just restricting that I'm not hearing people talking very loud, so I'll fix that later. Anyway, so SGD, of course, it's the main algorithm found in machine learning. And the idea is that because we are trying to optimize this empirical risk, if we have a very large data set, it gets expensive just to compute f and even to compute the gradient of f. And so the idea is to replace the full gradient by some stochastic estimation g of t. And we usually need two conditions or hypotheses on these stochastic estimates. One, it needs to be unbiased, so the expectation of g of t at theta t minus 1 given or conditioned on theta minus 1. It's a slight detail, but like the idea is that we only have theta minus 1, so we don't depend on any randomness that is within theta minus 1. It's just g of t might have some additional randomness from the sampling, but not from the actual theta of t minus 1. So the expectation of the gradient estimate is just the gradient. And we also ask that it's bounded, so g of t, gt of theta t minus 1 in norm must be bounded almost surely. So when you see almost surely, you should think, okay, in basically every single case except maybe like one exception. And so note that boundedness, you could think of it as saying that in some way the variance must be bounded, right? So in this case, if we look at let's say f being convex, so not even strongly convex, and b Lipschitz. So note that I haven't noted the definition of Lipschitzness, but b Lipschitz basically means the same as this thing being bounded, or the gradient, where the gradient of f must be bounded by b. So b Lipschitz, and then assuming that we're within some distance d of the optimal solution, and then g of t unbiased and bounded, then taking SGD with this learning rate scaling with 1 over the square root of t will give us the following convergence rate. Sorry, so for the expectation, there's a lot of impact. So the expectation of theta bar of t minus the optimal, I think it should be the parentheses are wrong here, but imagine this is the expectation of the difference between f of theta bar minus f of theta star, and it's going to be smaller than this constant times 2 plus log of t over the square root of t. And this theta bar is just basically the average over the thetas. So the individual theta values might not converge, but their average is going to converge to the optimal solution. So this is just the weighted average of the iterates of SGD. If we take a stronger assumption of I think strongly convex, mu strongly convex here. Again, sorry for the typo. Same assumption that B is Lipschitz. Then, if we add, say, a regularization term of mu over 2 times the norm, and again the gradient estimates unbiased and bounded, then doing SGD this time with the learning rate scaling 1 over t. Then we get another bound for the expectation over the weighted averages of the SGD steps, and then it's smaller than, again, something like log of t over t. So notice that this is a little bit better, because we have log t over square root of t, whereas actually, sorry, it's wrong. So this should actually be a little bit better, but we'll see that taking this kind of learning rate is not ideal. Yeah, it's shown in this situation, so it's again an experiment from the book, not on a neural network, but on a support vector machine, and they basically show what happens when taking this 1 over square root of t learning rate or the 1 over t learning rate, and you can see that as you take a lower value for mu, the 1 over t learning rate is a lot more jaggedy or fragile, whereas the 1 over square root of t stays pretty smooth. But again, like all of this, everything I'm talking about so far is just the nice convex case, so not even neural networks. Anyway, so a quick recap is that so we've talked about basically these two cases. So assuming I have convex and then non-smooth, although I haven't really talked about non-smooth, but it's fine. The convergence rate for gradient descent and both SGD is going to be 1 over square root of t. So to reach an error of, let's say, epsilon, I need to do 1 over epsilon squared steps to get within that. In the strongly convex case, it's a little bit better. Now it's basically, instead of square root of t, I get t. So now I need only 1 over epsilon steps to converge. If in addition I have smoothness, then at least for gradient descent it's even better. Now it's 1 over t squared. So now I only need like 1 over square root of epsilon to converge. But SGD is not that much better. But for the smooth and strongly convex, then I get like actual exponential rates, at least for gradient descent, and 1 over t for SGD. So again, like these are theoretical estimates, they're upper bounds. You can be quite far below these upper bounds in some cases, and it only applies in the convex case, which obviously is not the case for neural networks. So in this case, the non-convex case, which is what happens when you have a neural network of more than one layer, we have a lot fewer guarantees, but the best case scenario is basically that gradient descent to SGD is going to converge to a stationary point. And maybe, hopefully, you can assume that at some point it's going to be within a region of parameter space where it's locally convex, like within a small region. And then in principle you have the same theoretical guarantees, but it's not especially well understood or known. But anyway, at least for SGD, there's a similar result for gradient descent, but I'm just giving the SGD one. So assuming that f is L smooth, and I'm using this constant learning rate, and again unbiased bounded gradient estimate, then the expectation of f of theta t is going to be smaller than the expectation of the previous estimate minus gamma times the expectation of my gradient norm plus some additional term here, which is constant. So this does not guarantee that we're going to decrease the loss. In fact, because SGD is not a descent method, even in the convex case, it's not guaranteed to decrease, but at least in expectation, we have some play with that. We have sort of two different rates with similar readings. And so this lower one here, we can sort of think as it's saying, I'm taking the average of this over my whole, let's say, trajectory, and it's small. I think this is 1 over gamma t, times the initial estimate plus this constant. And so this says, well, you're not guaranteed to go to a stationary point, but at least one of your theta t is going to have a small gradient norm. But that's not enough to tell you that it's converged. So yeah, that's basically all the material I had for today. But it might be a bit disappointing because, well, we don't really know what to do for neural networks. But I may have some additional comments for that. Okay, any questions? Can you, sorry, can you talk a bit louder maybe? Or I'm trying, I can barely hear you. Not much better, but I think he'll still do. Okay. So yeah, so I didn't know about these papers, but yeah. Do you mind? Let's maybe putting the archive link in the chat. Might be interesting to see, but again, like, even though I've like turned all my volume to max, I can barely hear you. But yeah, I'm not entirely surprised that you can find some backtracking used in some places, but I think in general it is a bit too expensive. Right, because the general idea is that you have to evaluate your function at multiple points and say, okay, is this step good or not? And I think in like large scale workloads it's too expensive. But yeah, it'd be interesting to see streaming deep reinforcement learning finally works. Yeah, I'll check it out. Yeah, thanks for the recommendation. Okay. Yeah, if anyone has any other questions, maybe ask them over chat, because it's all questions now. I'm all out of slides. Okay, so the question is the inverse problem of trying to identify the objective function or optimize its use, given access to model parameters or outputs, either at the end or across all of training. And so to what extent there may be a crossover between the inverse problem and ML interpretability. I've never heard of this problem before. I feel like, but this is pure like guess on my part here, that if you have just a, like, let's say just a trained model, it's going to be pretty hard to guess how it was trained. Like, unless, let's say, you've like trained a lot of models and you have this intuition, but I'm not sure, like, theoretically you could solve that easily. And even like, yeah, even for the objective function, I guess that you're going to have those kind of problems. If you had, let's say, a whole training trajectory, it might be a little bit better. At least you could like check. Well, if you don't have the objective function, would you be able to do that? Yeah, I'm going to guess like you can maybe recover the objective function up to some like transformation. So at least perhaps a simpler case of the interpretability problem to consider that doesn't involve giant models and just involves lower dimensional optimization problems. Um, Right, so if I think of, say, uh, linear regression, let's say I have my parameters, like my objective function would be the outputs and the inputs. And I could imagine like applying some linear transformations on both the output and the variables that doesn't change the actual solution. So yeah, I'm not sure how to frame that as an interpretability problem. And even then you'd have a problem of like it's not clear whether the optimization or like what is the class of optimization function that you can hope to recover. But yeah, like it would be interesting to see like a more formalized version of this problem. Okay, but yeah, thanks for the question. Is there any other question for now? Well, doesn't look like it, so I think we can wrap it up for now. Thanks everyone for coming in and listening. Um, as I was mentioning at the beginning, but maybe not everyone heard of it or heard it. I'm not sure, like this might be the last math reading group, at least for quite a long while, because I have way fewer time to do this as I used to than I used to, and honestly, much less energy too. So, and because so far no one has offered to take it, like to continue it. Yeah, there might be a next one, but in quite a while. So this is, for all intents and purposes, maybe the last math reading group. So thank you at least for all for being there for the last one, or maybe the last one.